My name is David Roet and I work at the Flemish Environment Agency, mainly on topics related to air quality modeling, but I also like programming and playing around with data. In the Vacuums project, I mainly helped with programming the ESPs and also with setting up and configuring the data communication of the sensors. Today, I will be presenting the work done on the low-cost gas sensors by my colleague Christina Matthijssen.
Hi, in this presentation we will show the results and performances of 5 different low-cost nitrogen dioxide and ozone sensors used in the Vacuums project. More detailed information can be found in the 2 reports shown at the top. All of this work was done by my colleague Christine Matthijssen of the Flanders Environment Agency. After tests under controlled conditions in the lab, the different gas sensors were placed in the field, just like the PM sensors. All sensor units were co-located in shelters, towers, for more than 1 whole year at the urban background measurement site of VMM in Borgerhout, Antwerp. During the field campaign, the gas sensors were compared to the reference methods for nitrogen dioxide and ozone analysis. The sensors usually reported per second, but these were aggregated as minute, 5-minute, hourly and daily averages. The hourly level was chosen as the main aggregation level for most analyses. Here you see the division of the entire field campaign of 400 days into 2 parts from February 2019 until March 2020. The first month of operation was used to check the calibration of the gas sensors in the field. The remaining 1-year period was then used to evaluate the performance of the gas sensors using metrics like R-squared, between sensor uncertainty, mean bias and relative expanded uncertainty. Let's now start by looking at the results for the NO2 gas sensors in more detail. This overview shows the 5 different NO2 low-cost sensors that were used. We have the AlphaSense B43F, CityTech 3E50, and then 2 membrapores, the C1 and the C20. At the bottom you see the Envea care clip. The 4 sensors at the top report values every second, while the Envea care clip had a frequency of 15 minutes. As mentioned earlier, in both cases we aggregated to hourly mean concentrations for further analyses. So, what does the raw, non-calibrated signal tell us? Here you see scatter plots comparing the hourly mean values. On the x-axis is the reference motor, and on the y-axis the low-cost gas sensor. The black line shows the perfect 1-to-1 relation. We can roughly divide the results into 2 groups. One that exhibit a more or less linear relationship, and another group that clearly does not. The AlphaSense B43F also showed a lot of negative values in the measurements, as can be seen in the graph on the left. The Envea care clip is a closed system, so we don't really know what it is doing or which corrections are being used behind the scenes. One of the main questions for these NO2 gas sensors is whether there is a relationship with ambient conditions and ozone. These plots show the ratio of the sensor to the reference hourly NO2 values as a function of different ambient conditions for the AlphaSense B43F. The top left figure shows that this ratio is quite different at lower relative humidities, below 40%. And one sensor, the purple line, even behaves a little different from the other 4. In the bottom left figure, the ratio is shown as a function of temperature, and we start seeing changes for temperatures above 20 degrees Celsius. The blue and purple sensors behave different from the other ones. The figure on the right shows the influence of ozone, which, not surprisingly, looks quite similar to the one of the temperature. Let's now take a look at how we corrected for the influences of temperature, humidity and ozone. In the lab and during the calibration test, an orthogonal linear regression model was used, like the one shown here at the top. During the field tests, we explored different multiple linear regression models, MLRs, which are shown here. Let's first look at MLR2, which expresses the NO2 as measured by the sensor as a function of the NO2 measured in the reference station, the interferent ozone, the temperature, and relative humidity. MLR1 is the same as MLR2 except for the interferent of ozone. Applying these MLRs improved the results of our NO2 sensors greatly. Here, the effect of applying a multiple linear regression model is shown for the CityTech NO2 sensors. Of the 5 sensors, VQI1 and VQI4 gave very high values during the entire measurement period. These sensors were therefore not included in the analysis of the field data. As you can see at the top, there is almost no correlation between the uncalibrated sensor data and the reference data, as shown in the scatter and density plots. Due to the low correlation, the parameters of the linear regression are not well defined and were not calculated in the report. We see that when we apply MLR2, the results improve, as witnessed by the higher R-square and the shift and change in distribution of the density plot. But still we see that 1. There remains a big difference between the individual sensors. VQI5 clearly performs better. And 2. That all sensors keep underestimating, with mean biases varying between -28 and -21 micrograms per cubic meter. We would like to note that during the field campaign, these sensors were not oriented according to the specifications in the manual. It is unknown to what extent this orientation affected the measurements. Here we show the results for the Membrapore NO2 gas sensor. We see a very skewed distribution of the ratio sensor to reference before calibration. The low R-squared for these whales confirmed that there was no real linear relationship with only the NO2 reference. Calibration with MLR2 clearly improves the R-square and also the shape of the distribution. Still, the R-square remained rather low, and 4 out of 5 sensors kept underestimating on average, for VQK1 up to -22 micrograms per cubic meter. Did we see a noticeable degradation of these sensors over time? Here is an example of different behavior over time for the Membrapore C20 NO2 gas sensor. These plots show the time series of the reference monitor, the red lines, and the uncalibrated sensor data, the blue lines. At the top left is the behavior at the beginning of the campaign in 2019, and at the bottom right at the end of the campaign in 2020. If we look at VQL4, we see that there was a near constant offset at the beginning, but at the end the behavior became very erratic with lots of spikes. Now let's take a look at ozone low-cost sensors. This overview shows the 5 different low-cost ozone sensors that were used. The AlphaSense OX-B431, the CityTech 3E1F, the Membrapore C5, the Aeroqual SM50. The 4 sensors at the top report values every second, while just like for NO2 sensors, the NVIDIA care clip at the bottom, the frequency was 15 minutes. All measurements were aggregated to hourly mean concentrations in our further analyses. Here, the relation between the ozone measured by the reference monitor and the sensor is shown. 4 out of 5 sensors showed some kind of linear behavior, while the Membrapore C5 shows little to no relationship. One of these sensors, the Aeroqual SM50, performs very well out of the box with a high R-square of over 0.9 and does not need any kind of calibration. For the NVIDIA care clip, a simple linear relation model was sufficient. We do want to remark that this sensor measures both NO2 and ozone at the same time. Therefore, it probably already corrects internally for interferences of ozone measurements due to NO2. For the other three sensors at the bottom, the MLR2 model gave the best results. Here we show the results for the membrapore C5 ozone gas sensor. We see different biases and variances in distributions of the ratio sensor to reference before calibration. The scatter plots show there was no real linear relation with only the ozone reference. Calibration with MLR2 using the ozone reference, temperature, relative humidity and NO2 reference clearly improves the R-squared and also the shape of the distribution. Sensor VQM5, the one at the bottom right, performed worst with an R-squared of 0.3 even after calibration. Here are some of the main conclusions from the reports on the low-cost gas sensors. There are big differences in out-of-the-box performance. 3 out of 5 NO2 sensor types need a calibration with an MLR2 model to show correlation with the reference method. 4 out of 5 ozone sensor types show correlation with the reference method, and for one sensor type, calibration did not lead to better performance characteristics. For all NO2 sensor types, calibration with multiple regression model or MLR2 model improved the raw measurements, but there was no sensor type for which all individual sensors have an expanded uncertainty below 25% at the hourly limit value of 200 micrograms per cubic meter. For ozone sensors, the best calibration model varies with the sensor type. 2 sensor types have an expanded uncertainty below 30% for all individual sensors at a threshold value of 120 micrograms per cubic meter. The parameters of calibration models were determined for every single sensor of a sensor type. It is unlikely that one calibration function for different sensors of a sensor type can be used in the future. Multiple linear regression model improves the raw measurements for most sensor types, but meteorological and reference measurements are necessary. Limited lifetime and degradation over time remains an important issue.